Hello everybody, my name is Lê. I'm a PhD student in ECMA University of Brand 1. In this video, I'm going to share about our new research entitled Beyond Gap Screening for Lasso by exploiting new dual cutting half space. In the first section, I'm going to introduce about the screening method for Lasso problem. The motivation for Lasso is the so-called sparse linear inverse problem, in which we want to recover a sparse vector from a noisy linear system that's B equal to AX plus some noise. Here the sparsity means that there are only some coordinates of this vector that are non-zero. This problem plays an important role in many application domains. For instance, the non-zero coefficient of X indicates the important column of the matrix A. So this characteristic is somehow equivalent to what we call feature selection in statistics. Another applications is the compressed sensing techniques, and you can compress a very long sparse vector into a new vector of extremely small size. To recover this sparse vector, there are many methods. One of the popular options is to use Lasso problem. Lasso is an abbreviation for least absolute string selection operator. Here, to recover the sparse vector, we use X star, which is a minimizer of Lasso problem with objective function denoted by Px. It contains two parts. In the first part, we want to remove the noise by minimizing the distance between B and AX using square L2 norm. In the second part, we encourage the sparsity in X star using L1 norm. Here, lambda is just a parameter which controls the level of penalization. Since the problem is convex, a huge number of algorithms is available to solve this kind of problem efficiently. However, solving this problem in high dimension is still very challenging. In the last decade, a new method called screening was introduced, which allows you to solve this problem significantly faster. Basically, the goal of screening is to reduce the problem size by eliminating the zero entry in the sparse vector. Consequently, the corresponding column of A will also be dropped. So we only need to work with a reduced matrix of much smaller dimension. This leads to many advantages in terms of memory and computation. Therefore, the screening procedure is often used to accelerate many algorithms with significant improvement. So how can the screening achieve that goal? Without using mathematics, you can imagine that screening is a magic rule. So it will tell you if a coordinate of X star equal to 0, even if X star is an unknown optimal solution. For instance, if you get a message from screening that, hey, this one is 0, so what you should do is just to remove that coordinate. Otherwise, let's keep that one if you receive a message like, I don't know about this one. At the end of the day, you can significantly reduce the size of X star by using screening methods. Now, let's jump into the mathematical definition of screening rules. Actually, they rely on the duality structure of Lasso. By applying Fan-Chen-Rockefeller duality theorem, the dual problem of Lasso will be a maximizing problem of du, where u belongs to a dual feasible set, say big U. If you take a careful look into the U, you can find that to maximize it, you just need to minimize the distance from B to U. So the dual problem is actually a projection problem of vector B onto the dual polytope U. The connection between primal problem and dual problem can be established using the quantity called dual gap, which is defined as the difference between the primal value Px and the dual value du. This gap is always non-negative and it's only equal to 0 if X and U are optimal at the same time. You can also establish the relation between X star and U star by using KKT optimality condition. Here, you will see that the inner product between I column of matrix A and U star will equal to some value that belongs to the closed interval for minus lambda to lambda if X star I equal to 0. Otherwise, it will equal to lambda times psi of X star I. From this KKT condition, we can easily see that if the absolute value of this inner product is strictly smaller than lambda, then the first case must happen. It means that x star I will be 0. So this is basically the key idea of screening rules. However, the bad news is that we don't know the exact value of U star in practice. So it is necessary to have a more practical screening rules. To do this, U star can be replaced by an approximation which is nothing but a set containing U star. Such a set is called set region. In this case, to rewrite the practical screening rules, we just need to replace U star by U and take the supremum over the set region. Here, we emphasize the fact that the supremum can be evaluated explicitly if the set region has a simple geometry structure, like a bone in this example. It turns out that a good set region should satisfy the following three properties. First, it should be safe, meaning that U star must belong to that set. Second, it should be simple, so that the supremum can be computed easily. Last but not least, it should be as small as possible to best approximate U star. Some popular geometry regions are bone, half space, and dome. Here, a bone can be identified with two parameters being its center and radius. Its half space corresponds to two parameters being the normal vector and the intercept. For the dome, it is nothing but the intersection between a bone and a half space. So it can be parameterized by 4 parameters. In 2015, two set regions were introduced called gap bone and gap dome that rely on the dual gap in its definition. Note that both the regions are not only safe, but they all convert to U star. Seen here, the radius of gap bone is proportional to square root of the dual gap, which always convert to 0 in practice. So this is considered as the state-of-the-art property which separates the gap region from the others. In other words, we can say that gap regions are safe, simple, and very small. In the next section, we would like to introduce our new safe region called Holder dome. Our region is also safe, simple, and much smaller than gap region. To build the Holder dome, we use a lemma called the canonical representation of half space containing the dual feasible set. We saw that if U is a subset of some half space with normal vector G and the intercept L, then there exists some vector X such that G equal to AX and L is lower bounded by lambda L1 norm of X. Let L be equal to this lower bound, we can clearly see that U star will belong to this half space. Note that we can also prove this property by using Holder inequality here. So now we can construct our new dome region by taking the intersection of this half space with any other set-bone region. Here we choose C and R as the center and the radius in the definition of gap dome. In the definition of gap dome, we obtain a very nice theorem. The theorem contains two parts. In the first part, it states that Holder dome is safe since it contains U star. This is quite obvious due to the previous lemma. The second part of this theorem is quite more interesting. We claim that our Holder dome is actually a subset of gap dome. From this result, we can say that our Holder dome is safe, simple, and smaller than gap region. Here I also would like to mention that at the time of publication, we become aware of parallel works of Hiroaki and Makoto using a different technique and obtain equivalent results. So until now, we have seen that Holder dome is actually a subset of gap dome and all convert to U star. In this experiment, we are going to investigate their conversion speed. Here, let me talk about the setup first. We consider 3 problems corresponding to 3 different values of lambda, where lambda over lambda max equal to 0.8, 0.5, and 0.3. where lambda is just a threshold for lambda, that is defined as the maximum of ATB. For this problem, we plot the ratio between the radius of Holder dome and gap dome as a function of dual gap. As you can see here, when the dual gap gets smaller and smaller, the ratio converts to 0.7, which is strictly smaller than 1. So it means that our Holder dome converts faster than gap region. In the next experiment, we consider a more complicated setup with 200 problem instance with two types of matrix called Gaussian and Toeplitz, and three different values of lambda, corresponding to the cases that lambda over lambda max equal to 0.3 for the top row, 0.5 for the middle, 0.8 for the bottom. For this problem, we apply three solving methods by integrating three screening tests into Vista, which is a standard algorithm for solving Lasso. Its solving methods is provided a same computational budget as the number of plotting operators. We then evaluate the empirical probability that the problem can be solved as a function of required precision. The results confirm that using our Holder dome instead of gap region may improve quite significantly the probability that the problem can be solved. Finally, here are some of the references about the gap region, KKT optimality condition, and the paper of Hiroaki and Makoto. So thank you so much for your attention.